This meeting is being recorded.
At the end of Rhian's talk, I'll unmute everyone for the Q&A. And if you'd like to ask a question, could you just raise your hand? Thank you. So, hello, my name is Richard Greenwood, and it's my great pleasure to welcome our speaker for the 9th Ed Scott Lecture, Professor Rhian Jones. Rhian is currently based at the Department of Earth and Environmental Sciences at the University of Manchester. Recent studies involve cooking up experimental analogues of meteorites, which sounds intriguing. That was Rhian's description of this activity, by the way. Following an undergraduate degree in chemistry, Rhian did from Cambridge. Rhian did a PhD in geology at the University of Manchester. She then spent many years studying meteorites at the University of New Mexico, including a term as the curator of the meteorite collection in the Institute of Meteoritics. She's been extensively involved in the work of the Meteoritical Society, both as the treasurer and as the chair of the endowment committee. And here's the important bit: asteroid 5366 Rhian Jones is named after her. I looked it up, apparently it's an S-type, and so it will certainly be packed full of chondrules. In 2023, Rhian was awarded the Royal Astronomical Society Prize Medal, just to quote the citation, for her outstanding contributions in a series of closely linked investigations using chondritic meteorites to understand the composition and the formation of the first planetary bodies in the solar system. Rhian, of course, worked extensively with Ed Scott, and they published and edited many important books and papers together, particularly on the origin of chondrules, which of course is the subject of Rhian's talk tonight. So without further ado, I'll hand over to Rhian. Thank you very much.
Thank you, Richard. Can I just correct you on one thing? I went to the University of Oxford and not Cambridge.
I'm very sorry.
You have to get that one right.
Yeah, absolutely. Very, very important. Sorry about that.
Yeah, that's okay. Right. Is everything looking good?
Yep, it's looking great.
Okay. I'm just going to hide the meeting controls. Can you see my mouse?
Yes, we can, yeah.
Okay, good. Sorry, I wasn't in the right place. Okay, yeah. Right. Sorry, I'm just getting set up here. Okay, good. Is that working all right now? Is everything good?
Everything looks great, Rhian. Yes, that looks perfect.
Okay, well, thank you very much for the invitation to give this lecture, this Ed Scott lecture. I'm very happy to do that and very happy to honour Ed in this way. So the title of my talk is Chondrules and Their Importance in the Early Solar System. First of all, I'd just like to say a couple of things about Ed. I first met him in 1987 when I moved to the Institute of Meteoritics in Albuquerque. There's Ed on the front row, along with Horton Newsom, Klaus Kyle and Jeff Taylor, they were the core of the Institute of Meteoritics for many years. And Ed has always been just a really good friend, a lovely person, and it was a pleasure always to see him and Annalisa at Meteoritical Society meetings for many years after they all left and went to Hawaii. So Ed had an absolutely encyclopedic knowledge of all kinds of meteorites, in fact, probably every kind of meteorite there is. And he particularly made a lot of contributions to chondrule and chondrite research. And of course, that's what we're going to be talking about tonight. So you'll see his name popping up throughout this presentation. So just to set the scene of what we're talking about the protoplanetary disk, which is the original disk of dust and gas that was circling around the proto-sun in the very early stages of solar system history. So we're talking about the collapse of the molecular cloud into the proto-sun with the protoplanetary disk circling around it and jets emanating from the poles of the rotating proto-sun. And this picture for our solar system was what we looked like 4.6 billion years ago. So the importance of chondrules basically is that a significant mass of material in the inner regions of this disk could have been present in the form of chondrules. So that's the context of our interest in chondrules. So just first, before we get into chondrules, let's just think about they're sitting in chondrites, in chondritic rocks, and the different components of chondrites include chondrules, but also some other important materials. This paper by Ed and Sasha Crote on chondrites and their components, this review, is absolutely a great resource, a really important resource for just a good introduction to these different types of materials. So basically chondrules, you can see in these two pictures of two meteorites, an ordinary chondrite on the left and a CV carbonaceous chondrite on the right. Chondrules are the small round particles, little tiny beads of rock, and you can see that both of these types of rock are predominantly made of chondrules. We also have matrix, which is the material that sort of sits in between the chondrules. You can see there's quite a lot of it, particularly in the CV chondrite. Metal and sulfide, which you can see as the shiny white specks on the surface of this ordinary chondrite. And then these things called refractory inclusions, such as this big white blob in the CV chondrite here. So we're going to focus on chondrules, but the other components of chondrites also need to be considered if we're talking about the whole picture. When we talk about chondrules, they've been the subject of a lot of discussion and a lot of scientific papers, and also there are 3 books that focus specifically on chondrules, and I got them off my shelf and took this picture. And here are some papers that Ed contributed to these various books. Also, there's this volume of Meteoritics and Planetary Science, MAPS, from 2012, which is a focused volume on chondrules. And that volume arose from this meeting, which was held in New York in 2010, actually to honour Roger Hewins. And I like this picture because I put together all these different photographs of everybody at this workshop, which was a very lively workshop. You can see that there's a lot of frowns, a lot of hand waving, a lot of very earnest expressions on everybody's faces. And chondrules have always engendered a lot of debate, and there's just no doubt about that. I particularly like Connell Alexander's picture in the bottom right here. I think that's a great expression on his face. And Connell's paper in the MAPS volume was, at the beginning of the title, was Questions, Questions, and I think that just summarises the field of chondrule research. So this talk is going to ask a lot of questions, and it's not necessarily going to answer them. And the outline of the talk is summarised here. I'm going to, first of all, talk about what chondrules are and what they look like, and then what thermal conditions chondrules record. We'll talk about what mechanisms could have heated chondrules, how many chondrule-forming regions existed in the protoplanetary disk, how chondrules relate to refractory inclusions, and how chondrule properties inform models for the evolution of the protoplanetary disk and how important they are for planet formation. So just before we go any further, I just want to note that there's a lot of pictures of chondrules in this presentation. If they're not attributed to someone else, they're my own images, and a lot of the images don't have scale bars, and I apologise for that. It's maybe a bit lazy, but they're all chondrules around about 1 millimetre, so just take that as the scale bar. Right, so the first of our questions is, what are chondrules and what are their chemical and mineralogical properties? So let's start off by thinking about what a chondrule is. And they're basically, we can describe them as rounded, sub-ish or millimetre-sized particles that have evidence for melting. I like to add to this that they existed as droplets suspended in a gaseous medium. Some people might disagree with that. But the general picture is that we have a little parcel of dust, just a very small, fine-grained piece of dust. It got heated, it melted and formed this droplet shape object. And then as it cooled down, it solidified and mineral grains grew out of the cooling melt. So that's the sort of basic picture, and most people would agree on this. We might argue about the precursor material. But for the purposes of this talk, I wanted to clarify a couple of things. People have argued about whether a fragment of a chondrule can be classified or included as a chondrule. I say yes. I'm not going to talk about particles that have been heated slightly and sort of sintered together. The grains have been sintered together but not melted. Those are known as agglomeratic chondrules. I'm not going to talk about them. There are things called igneous inclusions, which are more like pieces of igneous rocks rather than free-floating droplets. I'm not going to talk about them. And I'm also not going to include metal particles in this definition. So I'm going to focus on silicate chondrules, excluding igneous inclusions. And it's really important to realize that everything I'm going to talk about is basically properties of chondrules that represent the most primitive, pristine protoplanetary disk material. So I'm not going to talk about material that has been altered by water or heat on chondrite parent bodies. And I'm just going to take that as an assumption for most of the things I'm going to talk about. So when we look at chondrules, we see a whole range of different textures and compositions. The picture on the left here is these are both ordinary chondrites, L chondrites. And the picture on the left is taken in an optical microscope. It's 5 millimeters across. And you can see that there's a huge range. Basically, every chondrule is different. They're not all the same stuff. And then on the right-hand side, this is an element map taken in the SEM, where iron is red, magnesium is green, and silicon is blue. And again, you can see that all the chondrules are different. You can't find two that look identical. And this is not just the texture, it's also the chemical composition. So the colors code the chemical composition. So that sort of sets the scene for the diversity of textures and compositions. So most chondrules are what we call ferromagnesian, meaning that they are rich in iron and magnesium, and their mineral grains, like olivine and pyroxene, have iron, magnesium, silicon, and oxygen in them. So this term ferromagnesian sort of summarizes all of that. They're millimeter-ish size. They have igneous textures, which means that they have textures that look like they crystallized out of this molten droplet. And they're generally rounded. They're not all perfectly circular, although we tend to show pictures of ones that are very perfectly round, but they certainly are not when you look in detail. And they basically consist of olivine and pyroxene crystals, such as this olivine here, set in a glassy or finely crystalline mesostasis. That's the name for the material that's interstitial to the olivine and pyroxene. A lot of them also contain little grains of metal and sulfides, iron, nickel, metal, and iron sulfides. So that's a sort of a standard picture of most chondrules. But there are other types of chondrules, and we shouldn't lose sight of that. And that includes aluminium-rich chondrules, such as this plagioclase-rich chondrule on the left. There are glass-rich chondrules, such as the one in the middle. And there's also chondrules that contain silica, which is perhaps more unusual. So there's a whole range of chemical compositions and minerals. But in general, we can talk about the main, the majority of chondrules, which are fairly similar in their characteristics. So porphyritic chondrules are the most common types of chondrules. And here's another paper by Ed Scott and Jeff Taylor from 1983, where they pointed out that in carbonaceous, ordinary and enstatite chondrites, there are chondrules that are very similar in texture and in composition. So they showed these very nice, very clear sketches of the difference between two olivine-rich chondrules that are both porphyritic, but this texture has high FeO content, and this one on the right has low FeO content. And on the top right-hand side here, you can see two chondrules that illustrate those textures. We now describe those types of chondrules as type 1 and type 2. So the low FeO ones are type 1 and the high FeO ones are type 2. If we just look at the type 1 chondrules, then these are the low FeO chondrules, and we further subdivide them by describing how much olivine and pyroxene there is. So if it's olivine, we call it A. If it's pyroxene, we call it B. And if it's got both in equal proportions, we call it AB. So we can see these different ways of describing these different ferromagnesian chondrules. Just to point out here, this mineral, clinoenstatite, is very unusual. It's pyroxene, low calcium pyroxene, that shows this very fine scale twinning when it's cooled very quickly from a high temperature, which is exactly what we see in chondrules. So another important thing about porphyritic chondrules is that they have mineralogical zoning. And this is an example from Jens Barosh's work, where we see the same chondrule, but it's sectioned sequentially through the chondrule. And those sections go through a shell of pyroxene in the first picture, and then about half and half pyroxene and olivine in the second picture, and a very olivine-rich image in the third picture. But those are all just cutting sequentially through a chondrule, which in 3 dimensions is a bit like an egg with a yolk in it, and we're just cutting through different parts of it. This is a very important observation, and a lot of chondrules have this texture. It's interpreted as condensation of silica into the chondrule melts, while the chondrule is molten, which increases the amount of pyroxene in the outside of it. So those are porphyritic chondrules, and then we have non-porphyritic chondrules, which include these textures: barred, radiating, and cryptocrystalline. Barred textures are the most photogenic chondrules, and sometimes we see multiple sets of bars, and I just threw these pictures in because they're very, very beautiful. So these chondrules are, these non-porphyritic chondrules are characteristic of having faster cooling rates, which we'll see in a few minutes. So I've already said that the chemistry of chondrules is very variable, and that's illustrated in the pictures on the top here. This is iron and magnesium contents relative to Ci chondrite for a range of chondrules in a range of primitive meteorites. And you can see there's a wide range of iron and iron to magnesium ratios, whereas the refractory elements, calcium and aluminium, there's a wide range in total amount of those elements, but they tend to be very fixed in their ratio, calcium to aluminium, and very similar to Ci chondrite. And the olivine compositions also reflect the range of bulk chemistry. So in type 1 chondrules, we have very low FeO contents in olivine. This is calcium content on the y-axis, iron content on the x-axis. So type 1 chondrules are FeO poor, and type 2 chondrules have FeO rich olivine. And the thing about type 2 chondrules is that we can have very strong zoning. So we could have a range of compositions within a single olivine grain from about 10 to 40 weight percent FeO. This is in CR chondrites in this example. Another thing on here is this forsterite relic grains, which I'll come to in a moment, and these have compositions very similar to type 1 chondrules. So our next question is what thermal conditions do chondrules record? And we'll talk about some other conditions as well. The first thing I want to talk about is the evidence for multiple heating events. The chondrule shown in this image consists of two zones. The inside zone is quite coarse and has big grains of olivine. And then there's a zone on the edge that has much finer grained olivine and pyroxene, and also quite a lot of metal. So the way we think this formed is we start off by making our originally inside chondrule by taking our dust ball, melting it and cooling it down to form our solid chondrule. But then while that is still in the same part of the protoplanetary disk, we're going to add a layer of dust. And then there's another event that heats it and melts it, but it only melts the outside part, and then that cools down, solidifies. So we end up with a chondrule, the original chondrule, with something that we now name an igneous rim. So this is evidence that we had at least two heating events that formed this object. So whatever made chondrules had to be a repeatable heating event. There's a second type of evidence for multiple heating events, and this is relic grains. So this is where we start off with our precursor dust, but it's got a larger yellow grain in this dust ball. When it gets heated, that yellow grain partially resorbs into the melt, but it's still there. And when it cools down, new olivine overgrows the relict, and we can point to these patches in the center of the grains that we know is evidence for the original grain surviving the melting event. So relic grains are various, and this slide summarizes the different types of relic grains. First of all, there's relic forsterite. So if we look in type 2 chondrules, which are FeO rich, this is a backscattered image, so the iron content of the olivine basically correlates with the gray level of the grain in the image. So the relict olivines are very forsterite rich, and they're very dark in the image. They're very magnesium rich, and then they are overgrown with more iron rich olivine that grew from the chondrule as it cooled down. So there's another example in this middle image here. So those are quite easy to spot in backscattered electron images. But if we want to look in type 1 chondrules for relic grains, then it's difficult because the olivine grains are quite uniform looking because they're all magnesium rich. But using techniques like cathodoluminescence, we can spot very bright regions in the centers of grains, which are relict olivine. And there's a second type of relic grain, which is called dusty olivine. This is a optical light image, and this is why these grains are called dusty, because they look dark in transmitted light. And in backscattered images, we can see this is a type 1 chondrule with a dusty olivine grain. This is what it looks like close up. So these grains are just dotted through with myriad tiny blebs of iron metal, which is precipitated out of this relic grain as the rest of the chondrule formed around it. So this relic grain was originally more FeO rich, and it got reduced during formation of this chondrule that it's sitting in. So relic grains and igneous rims are important observations for showing us that chondrule heating mechanisms were repeatable. Some other constraints that we can put on temperatures and times are that this is a chondrule where this is in reflected light, optical reflected light, and the bronzy coloured mineral in here is iron sulfide, troilite. And the presence of sulfur inside chondrules in itself tells us that the temperature of the region where chondrules formed had to be less than about 400 degrees in order to be able to incorporate sulfur. When we look at porphyritic textures, they tell us that we must have heated the chondrules too close to the liquidus. And then when we look at the presence of relic grains, then we know that they couldn't have been held at high temperatures very long because that would have destroyed the relic grains. And then we know that they had to cool fairly rapidly because that's what gives us things like barred olivine textures. The clinoenstatite that I pointed out earlier also indicates rapid cooling. The presence of glass, such as this pink material here, indicates rapid cooling. And chemical zoning in type 2 chondrules is also consistent with rapid cooling. But the other thing we can do is we can reproduce chondrules in the lab and be more specific about the formation temperatures and times. So this is an example from one of my students, Molly Wick, from quite a long time ago. This is a chondrule in a CR chondrite, and we reproduced the texture very nicely in the lab, so we know exactly the conditions that it needs to form this matching texture. So when we look at chondrules and we look at the thermal conditions for heating chondrules, we can think about the temperature that they were heated to and also the rate at which they cooled. So I've got time on the x-axis of this sketch. So we've got this solid precursor ball here, which gets heated up. And the critical thing is the temperature that they're heated to relative to their liquidus. The liquidus is the temperature at which a chondrule is completely melted. And this temperature varies depending on the composition. So we can't just say it's one fixed temperature. So if we heat them to just below the liquidus and cool them at tens to hundreds of degrees an hour, we get a porphyritic texture. If we heat just above the liquidus, but we've still got a few little grains remaining, and then we cool it fairly quickly, hundreds of degrees C per hour, then we might get a barred texture. And if we heat it much higher above the liquidus and then cool it very fast, that's when we would get these radiating or cryptocrystalline textures. So basically, it's the availability of nucleation sites that controls the resulting texture in the chondrule. So another thing we can learn from chondrules is, in terms of their formation environment, is the dust density in the chondrule-forming region. And we can get at this in different ways. This is a molten chondrule, and we can lose elements that are very volatile through evaporation when the chondrule is melted. But as the system is cooling, we can also condense elements into the chondrule melt. So some of the considerations that we make are we look at the fact that we can retain quite a lot of moderately volatile elements like sodium, manganese, phosphorus, potassium, and chlorine inside chondrule melts. This is an example of phosphorus zoning in a chondrule olivine, which shows very nicely that phosphorus was present in the chondrule melt as the olivine crystal grew. We can also look at the fractionation of stable isotopes, such as this list here, and see that there's limited fractionation of stable isotopes, which means that there was limited amount of evaporation from a chondrule melt. And we also have condensation of silicon to form the pyroxene shells. And all of these considerations lead us to the conclusion that chondrules formed in relatively dense regions of the protoplanetary disk, where the concentration of solids was thousands or even tens of thousands times what we would normally expect from the density of material in the disk. So chondrules are forming in a region where dust is concentrated, in other words. Another way that we can think about the density of dust in these regions is that chondrules stick together. And these examples on the right are what we call compound chondrules. You can see two chondrules outlined in yellow dashes in the top picture, where these two chondrules basically melded together when they were partially molten or plastic. And the same thing in the lower picture, this main chondrule has two little bubbles sticking onto the side of it, which are chondrules, secondary chondrules. So there must have been enough chondrules around in the region for them to bump into each other and stick together. Okay, let's move on to another question. What mechanisms could have heated chondrules? So we've talked about some of the constraints we have on the thermal conditions, but what can produce that kind of heating on the scales that we need to form large batches of chondrules? So this is a very controversial question, and this is one of the reasons why chondrules are always the subject of a lot of debate. So I'm just going to summarize some of the different ideas that have been proposed. The most favored mechanism for heating chondrules at the moment is in shock fronts, where we have the shock wave is accelerating the gas, and the frictional heating between the chondrules and the gas heats the chondrules. Plus, we also get heating from irradiation, infrared radiation, as the chondrule is approaching and departing from the shock front. But we might agree that chondrules form in shock fronts, but we don't agree on where those shock fronts happen. So one idea is that they happen as a result of gravitational instabilities in the disk. So this is an image that's 85 astronomical units across, and it's showing the structure of the disk with spiral arms, where we might get a shock front as these spiral arms sweep through the disk. Another possibility that's been proposed is that we have a planetesimal. In this case, this model has a 3,000 kilometer radius protoplanet that's ploughing through the disk, and it's creating a bow shock behind it. And the bow shock is the source of heat for making our chondrules. But there are totally different models around, and the main opposing argument is that chondrules form in impact events. So, but then there are lots of different ways of making chondrules in impact events. We can divide them into models that discuss the collision of partly molten planetesimals. So this is an animation of the collision of two planetesimals that produce a spray of droplets, which are going to turn into chondrules. And Ed and Ian Sanders proposed that have written papers and proposed this kind of model for splashing molten planetesimals together. And the cooling curves of, I should have said that in the previous slide on the shock front, that the cooling curves are calculated for this kind of environment, for chondrules that are produced in this type of environment. There's another type of impact event that's been proposed, which is impact jetting, where we have two solid bodies colliding with each other, and we get melted material splashing out from that impact. So this is an image of that splash from these two planetesimals that are crashing into each other, and here's the cloud of chondrules that results. Other chondrule heating mechanisms include radiative heating, where a red hot planetesimal passes through the disk, and just like if you were warming your hands in front of a fire, the chondrules experience that heat, and that's the source of melting. We also have the X-wind model, which was proposed for chondrules, but it's more favoured for CAIs and refractory inclusions these days. But this is a source of wind that lofts material from close to the protosun upwards, where it gets heated by sunlight. And lightning is another possibility that's been discussed. These models are out of favour at the moment for chondrule formation, but that's probably not the end of the story, because chondrule formation models come and go. This is a nice summary of the different temperature versus time curves that we would expect from some of these different models. And that's the kind of analysis that helps us distinguish between different models. A model has to account for all those observations of chondrule properties that I've already mentioned. There's one group of chondrites, or actually two groups of chondrites, the CB and CH chondrites, which are very closely related, and they are very metal rich. And there is agreement here that they formed from an impact plume. So this is where we have two colliding planetesimals, and this is a model from Rhian et al. On the right-hand side, where we have hot vapor in this expanding plume, which is very large. The scale at the bottom shows you it's 3,800 kilometers across. But evidence from these meteorites suggests that they formed in this kind of environment, and that we have silicate particles and metal particles condensing from this vaporized plume and then falling back onto the body, which was the parent of CB and CH chondrites. So that's something where people generally agree, but I think that if impacts were the source of most chondrules, then we would see more material like this. And although we do have materials that fit into this category, they're relatively rare compared with most chondrite groups. Right, so now we're going to talk about how many chondrule-forming regions there were in the protoplanetary disk. And this is important because we used to think that the protoplanetary disk was a single uniform disk and that we could make chondrules anywhere we chose. But more recently, it's become clear that the disk is divided up. And one of the really important observations is the evidence for variation in nucleosynthetic isotopes, which has been described as a dichotomy. And this is observed in multiple different isotopic systems. The classic plot is this one on the left, which is epsilon chromium-54 versus epsilon titanium-50. I'm not going to go into what that means in too much detail. The main thing is that there are two groups of materials in the meteorite collections. We call these carbonaceous chondrite materials. That's the group on the top right. And this other group is called non-carbonaceous chondrites, and it's referred to as NC and CC. So the non-carbonaceous chondrites includes ordinary and enstatite chondrites, as well as Rumaruti and Kakangari, and all the planets, and a lot of achondrite groups as well. So the general idea has evolved that, and this is this picture on the right is based on a study of molybdenum isotopes specifically. The general idea has evolved that the disk is divided into a red zone, which is the NC meteorites, and that's between the Sun and Jupiter, and a blue zone, which is the carbonaceous chondrites and related isotopic materials, which are on the other side of Jupiter, the far side of Jupiter. And this isotope dichotomy has resulted in a major rethink of chondrule formation, as well as planet formation and disk processes. But we might have these two separate types of chondrules, of chondrites, the NC and CC chondrites. But when people have looked carefully at individual chondrules, then we don't see this dichotomy. The compositions of individual chondrules spread much more widely than limited to those two so So I don't think we really know what that means yet. Some people in the audience might offer an opinion, but I'm not going to stick my neck out on that. The picture on the right shows the epsilon chromium 54 values, and again, you can see that there's no bimodal distribution here. There's a lot of overlap between the different groups, the enstatite, ordinary chondrites, several different groups of carbonaceous chondrites. And then what you'll notice here is that CR and CB meteorites are quite different. And this is going to come up again and again. The CB meteorites are those metal-rich ones that I talked about forming in impact plume. And the CR chondrites are more normal-looking meteorites, but they are very metal-rich, and they share a lot of isotopic characteristics with the CB and CH groups. So if we're talking about isotopes, we can also talk about oxygen isotopes, which are a very important part of understanding the early solar system. The oxygen isotope plot shows oxygen 17 on the y-axis, oxygen 18 on the x-axis. Again, I'm not going to go into the details of this. This is more looking at the trends. So if we look at chondrules from carbonaceous chondrites, and these are all type 1 chondrules, from carbonaceous chondrites, we see that they lie along this line, which has a slope of 1. It's called the PCM line, primitive chondrule minerals line. And there's a huge spread in oxygen isotope compositions, all the way from the composition of the planets, which is where these two lines cross, all the way down to the composition of CAIs, which is down at the bottom. And chondrules, and the same for ordinary chondrites, except they cluster more at the top of the line, but they do spread all down the line. But basically, chondrules capture a mixing process between an oxygen 16 rich component, which is the represented by the CAIs, and an oxygen 16 poor component, which is somewhere up the line, and we're not sure what that is. The best interpretation is that it's oxygen 16, sorry, that should say oxygen 16 poor, not oxygen 16 rich. Oxygen 16 poor materials, which could be ices derived from regions that have seen self-shielding processes. So chondrules sort of are a snapshot of the days when those two reservoirs were mixing. And different chondrite groups have distinctly different distributions of oxygen isotope compositions, which you can see in this plot here. So because of that, the differences between different chondrite groups, we can ask the question, did chondrules form in localized regions in the disk? And there's several lines of evidence that support this. One is that we find a different set of chondrules in each type of meteorite. Another is that each group of chondrites has a very specific chondrule size. And here, just to illustrate it, these are two carbonaceous chondrites, a CR and a CO chondrite, both 5 millimeters across. And you can see that there's a huge difference in the size of the chondrules. And this indicates that we have sorted objects by size, but it's not really clear whether we sorted the precursors of chondrules or the chondrules themselves after they heated. Some other ways that we can identify that we have different zones in the disk are that if we look at the manganese to iron ratio of olivine, specifically in type 2 chondrules, then we see that the ordinary chondrites, the carbonaceous chondrites, and again the CR chondrites are weird, but these different types of chondrules, even though they look very similar, they have different geochemical characteristics. And then we can look at the chondrule rims. Chondrules in CR chondrites, for example, commonly have igneous rims overlain with silica-rich igneous rims, whereas in CM chondrites, chondrules often have a very wide fine-grained accretionary rim. And these properties are very characteristic of each individual chondrite group. So there's quite a lot of evidence to say that we have a chondrule-forming region from which we form a parent body, and another one where we form another parent body. And all of these different characteristics that are listed in the box are very specific characteristics of each individual chondrite parent body. So we have this picture of the disk now that is divided into these different regions where different types of chondrules and therefore their chondrite parent bodies are formed. So the next question is, and there's only a couple of questions left. The next question is how chondrules relate to refractory inclusions. And for this, the first thing I want to talk about is the ages of chondrules. So we think about the ages of chondrules relative to formation of CAIs, and CAIs are a variety of refractory inclusions. We do this because for many, many chondrules, we have ages that are determined by the initial aluminium-26 to 27 ratio, which is a measure of how long after the start of the solar system, after CAI formation, how long after that the chondrules formed. So we're measuring a relative age. So you'll see on this graph on the left that we've got the aluminium-26 to 27 initial ratio on the left-hand axis, but on the right-hand axis, we've got the time after CAIs in millions of years. So it's 1 million years at the top, 2, 3, 4, 5 after CAIs going down the axis. And you'll see that all these different chondrite groups, we do have chondrite groups that are very well defined and different from each other in terms of their ages. Again, the CR chondrites are unusual, and they're similar to the CH meteorites in having very relatively young ages, forming quite a long time, about 4 million years after CAIs. The plot on the right summarizes the ages of ordinary chondrites in red, most carbonaceous chondrites in blue, and then the CR chondrites in yellow. And I'm just going to draw some lines on that to show the peaks of those ages, which are around 2 million years, 2.5 and 4 million years after CAI formation. There's also quite a spread within the groups. But basically, this is telling us that there's about a 2 million year gap between the formation of CAIs and chondrules. So that's a bit of a difficult problem to explain. But if we turn to measuring absolute ages with the lead-lead system, which is a very precise way of measuring the exact age of an object, and we relate it on this graph to the age of CAIs, given as 4567.3 million years, then these are the ages of chondrules, and you can see that there is no 2 million year gap. I'm going to put the same dashed lines on as I did on the previous slide, so that you can see that those were the peaks of the distributions in the previous slide, but the lead-lead ages of chondrules spread all the way back to the formation time of CAIs. The spread of ages in itself is a bit of a problem if we want to talk about localized formation of individual chondrite groups. But the fact that there's a difference between the lead-lead ages and the aluminium-26 ages is also the subject of a lot of debate, and I'm not going to go into that any further. One important thing is that if we look at the ages of core formation in differentiated asteroids, so iron meteorite formation, then we see that those ages are around 1 million years after CAI formation, and so they're older than most chondrules. And this sets up a conundrum because we don't know whether chondrules were being formed throughout this time interval of 4 or 5 million years, or whether the first planetesimals, which became differentiated, we don't know if they consisted of chondrules or not, because we don't have chondrules from that era. So looking at the lead ages is important to understand whether we had chondrule formation throughout this whole period, or whether chondrules were limited, like the aluminium-26 ages suggest, that chondrules were limited to later formation times. So there's other relationships between chondrules and refractory inclusions. For example, there are very rare examples where we see a CAI enveloped in a chondrule, which means that the CAI is a relic, like a relic grain, but this is a relic CAI. And we don't see the reverse. We don't see relic chondrules in CAIs. So this is consistent with the sequence of formation of CAIs preceding chondrules. There are also the aluminium-rich chondrules, which I mentioned earlier on in the talk, which have compositions intermediate between CAIs and chondrules. And so those are sort of transitional between CAIs and chondrules. The reason I wanted to bring up CAIs is because we have melted CAIs, which are called type B and compact type A CAIs. And these are also melted. So I don't think we really understand whether we had the same heating mechanism for these CAIs as we did for chondrules. But we can do experiments in the lab, like for chondrules, and reproduce the texture of an igneous CAI and determine the cooling history. This chart on the left shows the cooling curves for different chondrule-forming scenarios. I like the red one, the B curve, myself, because it has a cooling rate that decays as the temperature drops. But for CAIs, they cooled slower, and they cooled slower from higher temperatures. And it's not clear to me whether CAIs were heated and melted by the same mechanism as chondrules. We might need to call on a different mechanism for heating CAIs. So the final thing I want to talk about is how chondrule properties inform models for evolution of the disk and therefore for planet formation. And this will be brief because it's a huge subject. It's already been the subject of a couple of lectures in this series, and I'm sure it'll be the subject of many more. Basically, our protoplanetary disk models are now getting a lot more complicated than they used to be. First of all, the disk is divided by Jupiter into the inner and outer solar system, the non-carbonaceous reservoir and the carbonaceous chondrite reservoir. But it's also becoming divided into regions where we have collections of dust, concentrations of dust in different zones within each of these parts of the disk. And this is potentially where chondrule formation could take place, followed by quite rapid accretion in these what are called pressure bumps, where we get streaming instabilities that collect the material together in a very short space of time. This graphic is taken from a paper by Rufenacht et al., and I'm taking the liberty here of extending it by copying this section and adding another section further out in the disk, which is further out than Saturn. It's been suggested from looking at the returned material from asteroids Bennu and Ryugu that these form even further out in the disk, possibly beyond Saturn, because there's a lot of nitrogen which could be derived from ammonia ice. So this idea of the disk being not just segregated into two zones, but into multiple zones where different chondrite groups form is something that is being discussed a lot at the moment. So we think of CAIs as forming close to the sun, and then chondrules, we're very happy with saying that they form in the inner solar system, and they must have formed beyond Jupiter because that's where we've got groups of carbonaceous chondrites with a lot of chondrules in. But then as we go further out, how far out did chondrule formation processes go? Did we form chondrules in the Bennu and Ryugu region? Or if we see evidence of chondrule-like material here or in comets, is it just material that's been carried outwards from further in where it was formed, or did we actually get chondrule formation out in those zones? Those are questions that we don't know the answers to. Just very quickly, another idea, and this is just an example of a model. There are many different ideas and models out there, but this is a model where we're not just talking about what's happening at different distances in the disk, but we're also talking about how that evolves with time. So in this model, we've got, in the very early stages, refractory inclusions forming near the sun, chondrules forming in the inner solar system, the red ones, the blue ones are in the outer solar system, the carbonaceous chondrules. And then we have growth of planetesimals and protoplanets, by accretion of pebbles, which are slightly larger than chondrules, but small clumps of chondrules would be sufficient to contribute to these pebble growth models. I'm not going to talk about that any further in any detail, but these are different ideas that really emphasize the importance of chondrules, because new ideas for the evolution of the chemical composition of planets in the inner solar system have started to think about pebbles as being the main components rather than larger planetesimals. And this is getting close to the size of chondrules. So just to summarize some of the current questions about chondrules that I think are still quite lively topics for discussion. With the same old chestnut, what was the mechanism that heated chondrules? I think we should also ask ourselves whether CAIs were heated by the same mechanism, and therefore how that works in the context of the disk. How far out in the disk did chondrules form? How do we explain this age difference between CAIs and chondrules? And we still are not really sure whether chondrules existed before the planetesimals that went on to become differentiated planetesimals, or whether chondrules are a product only of the late stages of the disk. And a further question I'd like to ask is, do you think we will ever observe the chondrule forming process? There's just astonishing imagery these days of protoplanetary disks in the act of forming planets, but we have never observed a process which we can point to and say, this is making chondrules. So I just want to summarize with some thoughts about the importance of chondrules in general in the context of protoplanetary disks. They could have been the dominant solid particles, at least in the inner disk region, but also extending out beyond Jupiter. We don't understand the chondrule heating mechanism. We still are not agreed on what that is, but we can say that it must have operated in a similar way on similar materials over similar timescales over a wide range of heliocentric distances. And that in itself, I think, is quite an important understanding that we have to sort of fundamentally explain. We've got this diversity of chondrule populations in the different chondrite groups, and this suggests that we have this localized accretion, which might be consistent with current ideas about models that include streaming instabilities and pressure bumps in the disk. And chondrules might also be a critical component of planet building materials for growth via pebble accretion. So chondrules might have more of a significance in terms of planet building materials than we previously thought about. And just in general, understanding the details of chondrule properties is just really important for interpreting the early evolution of the protoplanetary disk and planet formation. And chondrules are not only fascinating objects in themselves, but they basically are ground truth for all these different disk models. So I will leave it there. I hope I haven't gone on too long. There's just so much to say about chondrules, and I'm very happy to answer any, or try and answer any questions from you all.
Rhian, thank you very much. I'm just going to unmute everybody, and also they can share their videos and ask their questions directly. But thank you very much for a fabulous talk.
You're very welcome. And I'd like to say that I know there's a lot of people whose names are recognised on the participant list, and I would love to say hello to all of you. Annalisa in particular, thank you for coming and for sitting through a lot of technical details, but I really appreciate you being here.
So Scott McGregor's got his hand raised. Scott, if you'd like to ask ask your question, sorry.
Sure. Thank you very much. Hey, excellent talk. And I was especially pleased that you covered CBs. You said at the beginning you were only going to cover silicate chondrules. And so I was pleased to see that. But anyway, a question, a lot of CBs, and if you look at Gujba, for example, it's a mixture of metal chondrules and also silicate chondrules. And I would expect if it was all from a plume, either they came from very different sources, or I would expect igneous rims around the silicate chondrules. And what do you make of that? And how do we get that mix of all metal and all silicate?
I don't know. I have no idea. I have a feeling that the CBA chondrites, like the one are you showing this picture?
Yes.
I think that it's possible that a lot of the metal particles are actually splashed in these meteorites rather than condensing from the vapor. But I think they're absolutely fascinating. They're amazing materials, but I don't understand what happens in this plume. I don't understand how big it is. I don't understand how you can get the range of size of particles and the range of properties that we see. We also have in the CBAs and the CHs, we have material that is more normal chondrite like CAIs and porphyritic chondrules. So that gets mixed in as well. And I think it's fascinating, but for me, completely unknown scenario.
Thank you for that. And I don't see any other hands. So one more quickie question.
Yeah.
We have a lot of CI material with chondrites in that. And does that give us any insight into that outer ring that you were talking about before? Or is it possible to derive anything new about the chondrules in CIs that are probably the furthest out, right? Or maybe the Y chondrites?
Yeah, I mean, I'm really speculating, putting that extra zone out there in that graphic. But I think that the Ryugu and Bennu materials, CIs, Sarah Russell has pointed out that they're really they don't have obvious chondrules that have been sitting there and affected by water. They're very tiny grains. There is some evidence for chondrule-like objects, chondrule objects, and individual grains that are derived from chondrules. But as I said, I'm not sure whether those have drifted out from further in, or if we could even get chondrule formation in those outer zones. And I don't think we know yet.
Thank you.
Thanks for your questions.
I just wondered if anyone else had some questions. If you'd like to raise your hand, go ahead. I thought I saw Alan Rubin there. I think I'm surprised he hasn't asked a question.
Me too. I must have convinced Alan.
Couldn't mind with raise his hand.
Answer a question. but I couldn't find the hand to raise. Didn't
Oh,
appear on my screen.
oh, I see. Okay. Well, Alan, is you there? Do you want to ask a question?
Technical issues. First of all, I wanted to say, Rhian, you did a fine job. I'm with you 85% of the way.
Well, that's pretty
Good.
good. I'm very relieved to hear that.
Considering, this is chondrules. So I just want to say that it's very good. My main concern is that I don't see how any bow shock could possibly be the main mechanism, because we have these microchondrules which are forming at the very periphery of pyroxene grains on some of these things, and they're forming by the hundreds in some cases, and also melting a pre-existing fine-grained FeO-rich matrix around these chondrules. And so I think we need a mechanism that's very repeatable and can heat the same object several times. And I don't think that, and I don't think bow shocks or any of these other shock heating mechanisms or impacts could possibly account for these.
That's fair enough. I'm not endorsing any particular model. I was just summarizing what they said. And I think that shock models are the most favored at the moment because they successfully reproduce the kinds of temperatures and cooling rates that we require. But I don't think any model is perfect.
Well, one other objection I have is the cooling rates themselves. I understand, and I've talked to you about this before, I don't see how you could get a 500 micron phenocryst growing in a melt at the same time as you're growing 4 micron or 5 micron euhedral grains of the same composition in the melt. So I think, as you well know, that some of these big phenocrysts have been melted a number of times. There's been a number of times that have a number of energy pulses or heating mechanisms that have account for these large phenocrysts to grow, that they did not grow all at once. I think that's more likely than not from my point of view.
Yeah, that's fair enough. Like I say, there's clearly evidence for multiple heating events, and we've had long discussions about how many of those there are, and this is not the place to get into that.
I understand, but I just wanted to tell everybody that chondrule formation and chondrule properties are a really significant problem, and there's a lot of contention at all the meetings, and the fact that Rhian and I can agree on 85% of this stuff is quite an achievement. So we're really making good progress on there, and I think you've done a really fine job.
Thank you, Alan.
Kun Wang had his hand up for a long time. So Kun, if you could go ahead with your question, please.
Hello, everyone. This is Katharina Lodders. I'm here with the Washington University Cosmochemistry group. And thank you for the very nice presentation. My question is, how well are the constraints on the cooling rates, and what are actually the mechanism controlling them in the protoplanetary disk? We have all kinds of models, but what are the key ingredients in the mechanism that control the cooling? Do we know anything about that?
Yeah, I mean, each of the different models has their own method of controlling the cooling rate. Maybe what you're referring to is that if you just have black body cooling, then it's going to be instantaneous. So you need to slow down the cooling rates. Even though they sound like fast cooling rates, they're really quite slow. So you need a mechanism to sort of damp down the cooling rates. So that could be a higher gas density, for example, or different. In each model has its own sort of solution to that problem, I would say.
Solution yet?
Well, I think each model, each proponent of each model would say they've solved it, because if you read the paper that describes that model in detail,
Sure.
then they will have an explanation for an appropriate cooling rate. Does that make sense?
Okay.
Yeah.
I'll get back to you on that.
Okay.
Sarah Stewart's had her hand up for a while there.
Hi, thank you for a great overview. I'm working on the physical models chapter for the next Meteorite in the Early Solar System 3 book.
Oh, lucky you.
And lucky me, I will add another mechanism to your list, which is work I published early last year on a hybrid version of impacts plus nebular shocks. In that we do like shock waves as physicists, and it provides a different scale and more diversity, I think, than the larger scale shock processes. But I agree with Alan that the data are rich and more than one thing is likely going on. One thing to remember in the debates about the physics that generates the melting is that many of these processes are happening. And the question is, what piece of what we're looking at is the remnant? And that is varying in space and time. So one thing is probably not the answer.
Yeah, I think that's a good point, actually. And it's clear that if we're going to accept that we have the CB chondrites forming from an impact plume, then we know that impacts will produce chondrule-like objects, even if we're not really sure whether we should include them as chondrules or not. But yeah, I think it's a matter of where and when these different processes operate and what conditions we need for each one to produce the right amount of material in the right parts of the disk at the right time. But yeah, I'm sorry I didn't include your model. There are probably other models I didn't include, and I apologize for overlooking yours.
Okay, I don't know if anybody else is having the problems that Alan had with putting his hand up. So if you'd like to ask a question, you don't necessarily have to put the hand up. If you've got something burning that you want to ask, Rhian, please go ahead. That looks about it. So if there's no more questions, Alan's got one.
I'd like to add one little thing. We know that there's in lunar regolith breccias, there's these impact melt spherules, which were called lunar chondrules back in 1970 after the return of the first Apollo samples. And so we have ordinary chondrite regolith breccias, which also form on the surface of their bodies. Even though periodic material is harder to melt than the basaltic material we found on the moon, there should be some fraction of the chondrules in ordinary chondrite regolith breccias, particularly, which were formed by impact melting. And I've always wondered if we could possibly distinguish those. I've failed to do so far.
Yeah, that's a good point.
Okay, well, I think perhaps we should, I don't know, we can give a clap to Rhian for a great talk, a really good summary of the field, I think. So
thank you.
Okay, thank you very much, and thank you everybody for coming to this today. We will have more Ed Scott talks coming up, and they'll be on the website very shortly. So keep watching for that. Thank you very much, everybody, for coming.
Thank you very much for the presentation. It was very amazing. Listen all these people who study for a long time. Meteorites. Hi from Chile. Bye bye.
Bye bye.
I think this might be the time to stop recording. I think.
I think so.
Yeah. So let's find that button. Okay. ultra thin.